Hi, good afternoon, everyone. My presentation is one of the last ones, so thank you all for being here. I'm Farnia. I'm a second-year electrical engineering major student. My project is Python simulations of mobile robots and core robotics algorithms. The project was under the supervision of Professor Atanesov and my graduate mentor, Arash. This project was done under the existential robotics lab at UC San Diego. So the project is closely related to the field of mobile robotics. And specifically, a mobile robot is a robot that is capable of moving around in its environment. In this field, a major interest of engineers has always been the making of autonomous robots that are capable of mapping their surrounding and having a better understanding of their surrounding environment. And this capability depends heavily on their robot's knowledge of every location on its path. So this is why simultaneous localization and mapping, also known as SLAM problem, has drawn immense attention in the field of robotics. The problem of SLAM is the building of an environment's mapping from a sequence of measurements by the moving robot. I know the picture is small, so I have an additional slide to show it. So here's an example of a robot that's trying to find its path through the rocks and simultaneously mapping it. And for all the robots that use SLAM to map their environment, the robot is left in an unknown and unexplored space, and it has to use its sensors and programmed SLAM algorithms to find its path through the environment by simultaneously creating a mapping of it. Going back to the presentation. Or poster, sorry. The SLAM problem is pretty complex, so we can break it down into the two subproblems of the robot mapping its environment and localizing itself in the environment that's yet to be explored. Mapping and localization together are the fundamental algorithms in the field of autonomous robotics. My research project specifically this year has been to study these problems, implement the localization and mapping algorithms in Python, and work with other members of the lab to prepare tutorials that introduce college students who are new to the field to the core robotics concepts that are altogether there to help them with understanding the field, and most importantly with the SLAM problem, which is an ongoing topic in research today. First, talking about the mapping problem. Mapping is the first problem that I got to explore in the first half of the project development. In a mapping scenario, we will be given the path of the robot at every time t, as well as some measurements about the obstacles in the room, and the output will be a visual or a mathematical representation of the map of the environment. We know that the space that the robot is placed in is continuous. There's an infinite number of points in that space that could be representing the environment, but to make it easier on the program that we're putting in the robot, we can discretize the environment into a grid that contains a finite number of cells that could either be represented as occupied or free to create the map. We have two options to represent every cell in the map. We can either represent it as a binary state, so 0 represents free space and 1 represents occupied space. But going with this method, although it's easy to represent every cell as either 0 or 1, we're kind of increasing the possibility of making mistakes and risking any mistakes that the measurements or any noises in the measurements could have. So the second method that we can go with is representing every cell as a probability value between 0 and 1. So 0.1, 0.5 would mean we're not sure if it's occupied or free. 1 would mean that if it's closer to 1, it would mean that it's occupied, and if it's closer to 0, it means that it's a free space. So the program that we have the robot use to create the map is going to be given the path that the robot travels in, which is going to be represented as a 2D array, with every element representing the position of the robot relative to itself in the unexplored environment. And when I say relative to itself, that just means that the robot has no initial understanding of the environment that it's been placed in. So the first point that the robot starts from in that environment is going to be the 0, 0 point on its path, or the map that's going to create. And let's look at the second diagram. So to talk about how the robot is measuring the different obstacles, looking at every time step here, the robot collects data from its sensors, and we assume that the sensors that the robot uses are light detection and ranging sensors, also known as LiDAR sensors. These sensors will use light in the form of a pulse laser to measure ranges or distances to the obstacles in the room. And these collected measurements are distances from the current position of the robot to wherever it has detected any obstacle. And because our robot is going to be able to measure multiple distances per time, we will have close to 251 measurements at a given time about what obstacles the robot is seeing at that given time. And in the right figure here, this one is representing the Bresenham algorithm that we're going to use to change the distances into actual mathematical representations of whether or not the cells are empty. And in this algorithm, we're given 2 points, the robot's global position and the obstacle's global position. And we give back an array of all the map cells in between. The map cells that represent free space are all the cells from the starting point to the end point, and the ending point is the only cell that's occupied. And here's a pseudocode of the mapping algorithm. As you see, the robot will go through every cell in the map. We define the map early before having it go through all these, this iteration. And we initialize all the cells to 0.5 because we don't know if it's occupied or free. And then through the algorithm, it's going to update the probabilistic value the cell holds based on the sensor measurements and the Bresenham algorithm. Here's some simulation results from running the mapping algorithm. This one is just a visual representation of the path that we're given at the beginning. This is the input that the algorithm receives. And then this is after running the algorithm. So here you see how purple is like the highest number, which is supposed to be closer to 1. This is not on a probability scale, but this is the path that we are definitely sure that it's free. And then occupied space is all these yellow parts. And then after turning it into a probability scale between 0 and 1, here's the final simulation result of a mapping algorithm, where the 0 represents free space and anything close to yellow or green represents occupied space. And once we have a mapping algorithm ready and we are sure that it works well, then localization is the problem, where we determine the position of the robot based on the given map. And once these two algorithms, we get them to simultaneously work together, we will have an autonomous robot. Some analysis of the work I've been doing in this lab, and the impact that the tutorials have had on the students. We use the tutorials in a 3-part lecture series that introduce grid mapping, localization, and SLAM in 3 different lectures. And all the implementations, simulations, and setup instructions are on GitHub. And this was a collective work between me and the lab members who had been working on the tutorials before I joined the lab. And the future work to complete the SLAM problem, because it has many different parts to it, is motion planning, which finds the shortest path from a starting point to a destination. I have been exploring A-star, AR-star, and other path planning algorithms. And the final work that I've recently gotten to explore is pi bullet simulations in the Python environment. I would like to thank my PI, my graduate mentor, and the GEAR program for this opportunity. And thank you all for listening.